Polynomial functions in one variable. So let's take a look at your average polynomial. Well, there isn't really such thing as an average polynomial, but an example of a polynomial. F of x is equal to 6x to the fifth plus 2x cubed minus 1. When we're looking at this, we notice that our highest exponent, the fifth power, is first, and then it goes in descending order. So getting smaller and smaller. So we have x to the third, and here's an x to the 0. That's just how mathematicians write things in standard form. Just like when you have the quadratic equations you've been working with, and you start with the x squared, move to the x term, and then to the constant term. So in this, that highest power right there, that highest exponent, is a 5, and that's called the degree of that polynomial. That whole polynomial is based on that highest power, or that highest exponent. So this polynomial has a degree of 5, or you could say it's a fifth degree polynomial. This number in front of the highest degree is called the leading coefficient. It's in front of everything else. The leading coefficient is 6. It can be negative or positive. In this case, it's positive. Now, to be a polynomial function, it must be all in one variable, in this case x. The exponents must be whole numbers, not fractions, and not negative numbers. It also must be a function, which is implied by the name. So let's take a look at some examples and see if those are polynomial functions. So our first one is a parabola, like our quadratic equation. It looks something like y equals x squared. So it's all in the x variable. It's x squared, no negative exponents. It is a function because for every x value, there's only one y value. So yes, this is a polynomial function. This over here is written as a polynomial function. All of the powers right here are whole numbers, no negatives, no fractions. So this is also an example of a polynomial function. G of x, down here, we have x to the third minus 2 times x to the negative 1 plus 7. We have a negative exponent. This is not a polynomial function. This is a lovely ellipse. First of all, it's not a function. And secondly, it's not a polynomial function because we have both x and y powers over there. And then over here, we have r of x is equal to the square root of x plus 5. Now we could rewrite this as x plus 5 in parentheses to the 1/2 power. That's what that square root means. So since it's got a fractional exponent, it is not a polynomial function. Here we have kind of a sideways parabola, something of the form x equals y squared. So that's also not a function because for an x value, I can actually find two y values, not a polynomial function. Over here, I have h of x equals 1 over x. This x is actually to the negative 1 power. I could rewrite this as h of x equals x to the negative 1. Since we have a negative exponent, this is not a polynomial function. So when we look at polynomial functions, we can actually classify them. Mathematicians love to classify things, and so they've also classified polynomials. So this is the type of polynomial, example expressions, and the degree. The degree, remember, is the highest exponential term that's in there. So the highest exponent. So here we have a constant. The exponent right here of the x is actually just a 0. X to the 0 power is 1. Degree of 0. Linear, you're very familiar with. I probably know about that since pre-algebra. X plus 8 is an example. The degree is 1 because this is like x to the first power. Quadratic, we did a lot of those, looks like parabola. And we have 3x squared plus 4x minus 3, degree 2. Cubic, we haven't done a whole lot of, but also the highest power right there is a 3, degree 3. Quartic, same thing. We have our leading coefficient is negative 3 in this case, and that's a degree 4. Quintic, leading coefficient of negative 17. Our power is 5 here, and so our degree is 5. Now, once you get past that, I think that mathematicians have just decided to call them all polynomials. So these are kind of like the middle names of the polynomials to just specify them. They're all polynomials. But once you get past 5, you really, mathematicians really just call that a polynomial. And I kind of liken that to having lots of children, probably past 5, don't give them middle names anymore. So then let's take a look at some of our familiar polynomials that you've dealt with. So a constant is just f of x equals 4. That's any vertical line. You can't have a horizontal line because that wouldn't be a function. That is a 0-degree polynomial. Linear, you're very familiar with. This looks like it's got a slope of 2, and it's a degree of 1. The leading coefficient here is 2. Notice that's what makes the slope positive or negative, is that leading coefficient. And that determines something called end behavior. So end behavior is what the polynomial is doing kind of on the extreme ends. So as x gets really positive or as x gets really negative. Well, in this case, it's pretty easy to see. As x gets really positive, y gets really positive. As x gets really negative, y gets really negative. So we can kind of denote this like this. On the positive side, on the right side, we've got an arrow going up, meaning that my y values are getting more and more positive, and an arrow going down on the left, meaning my y values are getting more and more negative. A quadratic. So f of x is equal to x squared. That's our pretty basic one. We've got the vertex at 0, 0. It's a degree 2. Notice it's an even degree. That's going to be important a little bit later. And the leading coefficient is 1. Even though there's nothing written there, it's an implied 1. Now the end behavior here is a little bit different than our end behavior for our line. Notice our end behavior is the same as we go more and more positive on the x-axis and as we go more and more negative. Well, if you think about it, if you're plugging in negative values and you're squaring them, you're going to get positive values. So my end behaviors are going to be the same. They're both getting more and more positive. So I have an arrow going up this way and an arrow going up that way. And that's what it's going to look like at the end. Now, if I look at another quadratic, pretty similar, except for I have a negative leading coefficient. My leading coefficient here is -1. I've shifted the parabola up 2, and I can see right here it's got 2 roots. Remember, a parabola can have either 0 roots, or it can have 1 right here, or it could have, and that's a double root, or it could have 2 roots right here. So here the end behavior is a little bit different too. Now the x squared, remember you're squaring numbers and you're always going to get a positive, but then you take the opposite. That's why the end behavior here is both as x gets more and more negative, y gets more and more negative, and as x gets more and more positive, y gets more and more negative. So as x gets negative, y gets negative. As x gets positive, y also gets negative because I'm taking the opposite of those positive values. Now let's look at polynomials you're probably not quite as familiar with. So here I have cubic polynomials, and this is about as simple as you can get to be a cubic polynomial. F of x is equal to x cubed. Now I've plotted some values on here, and it's very interesting, different than our x squared. When we put in a 1 right here, we get out a 1. So 1 cubed is just 1. -1, we get out a -1. So that's a little bit different. So let's go ahead and plot these. Looking a little bit like our line, but then as we put in a 2, we go really high. We go up to 8. And as we plug in a -2, we're going to get a negative value, and that's a -8. Now our cubic looks something like this. Not a great cubic. Okay. Looks something like this. So our x cubed looks like this. It's got a degree of 3. Leading coefficient is positive. And our end behavior looks a lot like our positive slope line. Now, if something's linear, remember its degree is 1. So it also has an odd power. So if you imagine our line, when the leading coefficient was positive, we have a positive slope. And our end behavior, as x gets more and more negative, y gets more and more negative. As x gets more and more positive, y gets more and more positive. So our end behavior looks a lot like it did with a line. Now what happens if we change this f of x just a little bit and make it the 1 a -1? So change the leading coefficient to a -x cubed. That means we're taking the opposite of whatever x cubed is. So when we put a 1 in and we cube it, we get a 1, but then take the opposite, and we get a -1. Same with -1. Take a -1 cubed, get a -1, take the opposite of it because of the leading coefficient, and we get a positive value. So if we do the same thing with 2 and -2, we see a very similar graph, but we're taking our y values that used to be negative, and this opposite is going to make them positive, and the ones that used to be positive, we're making them negative. So this end behavior looks a lot like a line with a negative slope. A line also has an odd degree. So my end behavior here, as I get more and more negative, I'm going to get positive because I'm taking that opposite. As I get more and more positive, I'm going to go negative because this x cubed will be positive, and then I take the opposite. Now let's look at a cubic that's a little more complicated, our h of x here. Now here I have it in factored form. This is not standard form for a polynomial. This is standard form for a polynomial, but I could take these and I could distribute them out, and I could get, right here is my difference of squares and my x plus 1, distribute here, and I could get both forms. These are both the same polynomial. This one helps me look at roots, which is why I wrote it like this. So it helped me come up with a nice polynomial. So my roots are when I can make this h of x 0, which is x equals negative 3, x equals 3, and x equals negative 1, which I denoted over here and plotted on my graph. These I counted by 5s, and these I just counted by 1s in order to fit everything. This form helps me find the y-intercept. Put a 0 in for x, and I get a negative 9 out for my h of x. So when I'm plotting these points, I kind of have this weird thing going on here. I kind of want to know what's happening in between these 2 points in order to really figure out how to graph it. So I chose a 2 and a negative 2, put them into either this one or this one, doesn't matter, and I ended up, when I put a 2 in, I got negative 15, so right here, and when I put a negative 2 in, I got 5. So very interesting so far. Now as I get really negative, as I choose negative numbers that are really big, well, I chose negative 10, that's not really big, and so you can imagine what really big numbers will do. But if I take a negative 10 and I cube it, I get negative 1,000. Now even though I still have a plus 10 squared, that's only 100. These other terms are really going to be overshadowed by this highest exponent right here, this highest 3. So when I take something to the third power, that's so much more than just to the second power. It's going to overshadow it. So if I take a negative number to the third power, I'm going to get a negative number. So my end behavior, as I'm getting more and more negative, my y values are getting more and more negative. And same thing is true with our positive. When I take a positive number and cube it, it's going to be a really big positive number if I choose a really big number to put in there. Doesn't even matter what these other terms are, they're overshadowed by it, and I have a positive line right here. And so this positive values as x gets more and more positive. So degree 3, it's an odd degree, which means it kind of has similarities to a line. So if you imagine the leading coefficient is 1, which means it's positive. So it's kind of like, I think of a line behavior because it helps me determine what my odd degree behavior is going to look like. So as I get more and more negative, this gets negative. As I get more and more positive on the x, my y gets more and more positive. Now let's take a look at even more complicated, strange things, our quartic. So I did the same thing. This is factored form, plotted my roots right here. These are difference of squares right here. And then I went ahead and distributed, and I have my degree for polynomial in standard form. It's even, so it's probably going to remind me of a parabola because this 4 does whatever, takes that number, takes it to the 4th power. So if it's a negative number, it's going to give me a positive number. So a negative 10 times a negative 10 times a negative 10 times a negative 10, that's going to give me a positive value. The same is true with my positive values. So here I have my roots plotted. I used this form right here of my polynomial in order to find my y-intercept. I have that plotted right here. And as x gets more and more negative right here, the values of negatives get bigger. With my negative 10, remember I said this is going to be a positive. So my end behavior I know is going to look like this, right? And then here I know this is going to get more and more positive as well as x gets bigger and bigger. But in between here, I might not know. So I might want to try like a 3 and a negative 3. So if I try a negative 3, I get out a negative 35 and a positive 3. I'm going to get a 35, and that's just substituting that value in. And so it's going to look something like this. So kind of like a weird W. Maybe a little bit smoother there. It's not very smooth. So some sort of weird W. Now my leading coefficient is 1, which means it's positive. So right here I'm taking positive values. If x is negative, I'm still going to get a positive value out. But if I look at g of x and change it just a little bit, I change the leading coefficient to be negative, multiply all of this by negatives, same sort of thing, taking this and making it into standard form. And I take the opposite of each of these terms. So now let's see what it looks like. My zeros are the same, so I plotted them. However, my y-intercept is going to be at negative 64 this time. So my end behavior, if you look at this, I'm going to take these negative numbers to the 4th power, which is going to give me a positive value, and take the opposite, which is going to give me a negative. And if I do the same thing with my positives to the 4th power, I'm going to make a positive number, and then take the negative. So my end behavior is going to be getting more and more negative as I go both to the left and to the right. So let's go ahead and plot what we know. Oh, let's check too. If I check a 3 and a negative 3 right here, negative 3 and 3, I'm getting out a positive 35. So 10, 20, 35. Let me just really get there. Okay, 35. Okay, so here we go. I'm going to get more and more negative up here, all the way down. I counted by tens here, back up and down. So it looks a lot like this one, and only instead of a W, I've got a nice M. So my end behavior, as I go left, my y values are going to go down and down, and more negative, and the same thing happens on my right. So when you have these degrees, these even degrees, your end behavior is going to be the same. The way it determines whether it's going to get more and more negative or more and more positive is that leading coefficient. That's what's going to tell you. So let's look really quickly at a quintic. Y equals x to the 5th. Looks a lot like x to the 3rd, and we would assume that because it's an odd degree power. So if we imagine our line right here, our leading coefficient is 1, so it has the same kind of end behavior as our line to the our first degree one. But this one's a 5th degree, it's odd. If we put in a 1 here, 1 to the 5th power is just 1. So it's looking a lot like x cubed, but if you take the fractions, the fractional numbers and plug it in, you'll see a little bit of difference there. And also if you plug in a 2 or a negative 2, because 2 to the 5th power is 32. And so it's really jetting up there. And negative 2 to the 5th power is negative 32. So same sort of thing, our end behavior, as we go further and further negative, our y values get further and further negative, and as we go further and further positive, our y values get more and more positive. Now let's take another look at a different quintic. Now this isn't in factored form, this is just sort of to show you what could happen here. I can have up to 5 zeros. I can't have any more because when I factor it, I'm not going to get more than 5 binomials. And so, or when I take the quadratic formula, the most I can, or use the quadratic formula, the most I can have are 5 zeros. I could have less though. Like look at this one up here. I only have it crossing once. And we can't have double roots. If you imagine taking this graph and shifting it up, you can see that you could possibly only have 1, even though it's a 5th degree polynomial. So my end behavior is opposite, just like all of my other odd polynomials. And as I get more and more negative, I get a negative number here, and then I'm taking the opposite. Remember, this overshadows all of these other terms as we take really large negative, well, not large, small, I guess, negative numbers. And the same is true over here. As we take really large x values here, I'm going to take it to the 5th power and take the opposite. So I'm going to get negative over here. So this is what my end behavior looks like. Now let's go ahead and take these and see if we can go the opposite way. Given the graph, what can you say about them? So this first graph right here, we can tell right away that it's going to be an even degree polynomial. It's not an even function, that has a whole other definition for it, but it has an even degree. So it might be x to the fourth. It might be bigger than x to the fourth. It can't be smaller because I have 4 zeros I see here, but it can be a bigger degree, but it has to be even. Also, my end behavior tells me that I'm getting more and more positive on both ends. And I kind of imagine it as a parabola because it has the same end behavior. So I know that that's going to be a positive leading coefficient. This one I can tell is going to be odd. It's going to have an odd degree in the polynomial. And so it's going different directions. As I get more and more negative, my y values get more and more negative. So that means it's going to be just kind of, and I imagine the line because it does the same end behavior as these odd degree polynomials. And I imagine the line and I know it's going to have a positive leading coefficient, right? Because I get more and more positive, and I'm going to be, as I go positive on the x-axis, I'm going to get more and more positive on the y-axis. This I know is going to be this kind of weird Hardy thing, is going to be a even degree polynomial. Now, as I get more and more negative, I get negative, and more positive on the x-axis, I get more and more negative on the y-axis. So I know my leading coefficient, just like in a parabola, when it scoops down like that, is going to be negative. This one, our last one, you can probably guess what it's going to be because I wanted to show you all the examples. So this right here, it goes positive as we get more and more negative. That means we're really taking the negative of the negative numbers. And so I know, first of all, it's going to be an odd degree polynomial. And secondly, I know that it's going to be a negative leading coefficient. And again, I imagine the end behavior of what the line does to kind of help me out. And so if I have a line that does that same behavior, it's going to have a negative slope, which is the negative leading coefficient. So now you know a little bit more about polynomials.